Hi everyone, welcome into lecture number 13 of differential equations. This lecture is on the variation of parameters method for solving a non-homogeneous second order linear differential equation. So let's work through the details of the derivation of this method, and then we'll just do a couple of examples once we understand the method, and we'll go from there. So for this method, we are going to suppose that we have a linear differential equation that is of the following form. So suppose the linear homogeneous differential equation y double prime plus p of t y prime plus q of t times y equals 0. Let's suppose that this has the general solution of the following form. So the form of this general solution, of course, is going to be, it's a second order equation, right? So it's going to be y of t equals c1 y1 of t plus c2 y2 of t. And for this to be a fundamental solution set, the y1 and the y2, then of course we have to have that the Wronskian of y1 and y2 is not equal to 0. Okay? So that means that y1 and y2 form a fundamental solution set for the homogeneous linear differential equation. All right, and what we're going to do is try to build a solution of a non-homogeneous equation with the same left-hand side. All right, so now that's the next step. Let's consider the non-homogeneous differential equation given by, again, the same left-hand side, y double prime plus p of t times y prime plus q of t times y, but this time the right-hand side will be equal to some function g of t. Remember, it's a linear differential equation, so the right-hand side is only going to depend on t, but in this case it'll be a function that is not the zero function. What we're going to do is we are going to guess that the solution of this non-homogeneous equation is of the form very similar to the homogeneous solution, except in the name of this method is variation of parameters. So we are going to assume that these constants, the c1 and the c2, these are the parameters in our solution. We're going to assume that these are allowed to be functions of t, and therefore they can vary, right? If they're functions, then they will vary. And so that is pretty much the main idea of this method, and we have to work through all the details of it, but we are going to guess that the solution of this non-homogeneous DE is of the form, so we're going to guess that it's y of t equals, and so I'm going to allow these parameters to vary, these constants, so I'm going to replace them with functions actually. So I'm going to call it u1 of t times y1 of t plus u2 of t times y2 of t. All right, we'll call this equation star. We're going to have a bunch of equations that we label so that we can refer to them later in this derivation. So this is the main idea. Now what we want to do, of course, is take the derivative of this equation and see what we get when we plug back in. Take the derivatives, I should say. Let's start with the first derivative. So taking one derivative, let's see what happens here. We're going to get some criteria for these functions u that we'll work with from that point on. So when we take the derivative, now that these are functions, we have to apply the product rule to each one of them, right? And so I'm going to do it in a way that's going to maybe look a little bit weird, but I'm going to write y prime of t. The first thing I'm going to do is allow the derivative to hit each of the y functions, okay? So I'm going to write this as u1 of t times y1 prime of t plus u2 of t times y2 prime of t. But of course that's not the whole derivative, because these derivatives have to also hit the u functions, right? So after this I'll go through and hit the u functions. So then it's going to be u1 prime of t times y1 of t plus u2 prime of t times y2 of t. All right, and the reason that I've separated it out this way is because now one of our criteria in our solution is going to be, we're looking for these functions u, right? The coefficient functions u. That's the main idea. Maybe I didn't make that clear. But if we can determine these functions u, then we know the solution, right? Because we already know y1 and y2 in this scenario. We are assuming that we have our fundamental solution set up here, right? So if we can determine u1 and u2, we'll have our solution. So one of the criterias on these functions u1 and u2 we are going to set is that this, we want to set the criteria that this portion here, u1 prime y1 plus u2 prime y2, that this must be equal to 0. So this sum right here should be equal to 0. So that's going to be, we'll call equation 2 star. That's going to be one of our equations that's going to help us determine the u1 and u2. All right, now that we've done that, that means, by the way, that our first derivative is actually only this part, right? Because if we set this equal to 0, that's gone. And so when we take our second derivative now, we're only going to have to take the derivative of this portion. All right, so now we'll go back and we'll take our second derivative. So I'll say taking another derivative here. Taking another derivative, here's what we end up with now. This is going to be y double prime of t equals, so now we can go through the same kind of logic, but actually we don't need to. So let's just go through and take the product rule the usual way. So this will be u1 prime times y1 prime plus u1 of t times y1 double prime of t. That's the product rule in the first term, right? Plus then the second term is going to be u2 prime of t times y2 of t plus, sorry, y2 prime, right? y2, I already had a prime, plus u2 of t times y2 double prime of t. So there's our second derivative. And now what we want to do is plug these into our differential equation. So we want to plug the second derivative, the first derivative, but only the pink part here, right? And then the function itself into the differential equation right here. And we want to see what happens, right? So in doing so, we get, so plugging all of these in, and if you can pause the video here for a moment and work this out yourself. I'm going to write this in a grouped form. So plugging in to the DE and grouping, all right, so in grouping by these functions u1, u2, u1 prime, u2 prime, etc., we get the following. All right, and again, pause the video for a moment and check this if you need to, but we get the following equation now. So u1 of t times, this is going to be times y1 double prime of t plus p of t, y1 prime of t plus q of t times y1 of t. That's all times u1 plus u2 of t times y2 double prime of t plus p of t y2 prime of t plus q of t times y2 of t plus, then there's a couple more terms. The next two terms, or the next few terms, are u1 prime of t, I'll keep writing all this here, of t times y1 prime of t plus u2 prime of t times y2 prime of t, and then the right hand side is of course g of t. We plug this into the non-homogeneous equation. All right, so now look what happens here, right? We've got a couple different things here. This combination right here, remember y1 is a solution of the homogeneous equation, right? So because of that, this portion is equal to 0. Similarly, y2 is also a solution of the homogeneous equation. So this is all equal to 0, right? And these two terms now are not part of this equation anymore. All that's left is this line. And so this line is going to be what we'll call equation 3. All right, so let's highlight that as well. We've got a lot of highlighting going on. Why stop now, right? So we'll make this one magenta as well. We set that one yellow up there. Let's make this one yellow so that we have consistent coloration here, right? So the equations then for the u1 and u2, actually the equations that we have are for u1 prime and u2 prime as combinations of y1, y2, y1 prime, y2 prime, right? So we have two equations. We obtain this, what we're going to call a system of equations, actually. We're not going to call it that. It actually is, right? So this is the key here. So equations 2 and 3 are going to become a system of equations for our unknown functions u1 prime and u2 prime, so the derivatives of our unknown functions. So we now obtain a system of equations remember, we know the functions y1 and y2, so we also know their derivatives, right? We know y1 prime and y2 prime. So our system of equations is for y1 prime, u1 prime and u2 prime. And we get these from the equations that we called 2 star and 3 star. So let me write down the system of equations itself, and then we can try to question how we would solve this, right? But the equations are u1 prime times y1 plus u2 prime times y2. That one was equal to 0. That was equation 2 star. We set that equal to 0. Equation 3 star is u1 prime y1 prime plus u2 prime y2 prime, and this one's equal to our function g of t, right? So now these are equations of functions, right? But we can write this actually as a formal matrix equation. So in matrix form, I'll say this becomes the following, right? So notice that the unknowns are u1 and u2 prime, u1 prime and u2 prime, and then the coefficients are actually the y1, y2, y1 prime, y2 prime. So in matrix form, it's going to look like this: y1, y2, y1 prime, y2 prime. All right, the unknowns are going to be u1 prime, u2 prime, and then the right-hand side is going to be this 0 and g. Okay, so we can now regard this, like I said, as a matrix equation: a times x equals b, right? So, and from here, we can use Cramer's rule to solve this. And we reviewed Cramer's rule in the last lecture, and this is kind of the reason why we reviewed it in the last lecture, right? So Cramer's rule gives us a solution to this. So Cramer's rule gives us the solution, right? And the solution is going to be the following. It's going to be that u1 prime is going to be equal to, so I call this a right here, right? So it's going to be the determinant of a1 divided by the determinant of a, and u2 prime is going to be the determinant of a2 divided by the determinant of a. All right, we need to write down exactly what these are, right? So a1, the matrix a1, remember how this works in Cramer's rule, is we replace the first column, 1, right, the first column with the vector b. So this is going to be 0 and g, and then the second column stays the same, so y2, y2 prime. And so this means that the determinant of a1 is going to just be negative y2 times g, right? Negative y2 times g. Similarly, a2 we get by replacing the second column, so y1 and y1 prime, that part stays the same, and then we replace the second column with 0 and g. And that means that the determinant of a2, this is going to be the product, positive, right, y1 times g. All right? Then, of course, what's a, the determinant of a? Well, that's just the Wronskian, right? So the determinant of a is the Wronskian. So this is our Wronskian function, which we already assumed at the very beginning here was not 0, right? So we can divide by it. So we can definitely solve this system, at least formally, at least to this point, right? All right? So, taking all of this into account, what we've obtained is that our derivatives of our coefficient functions, u1 prime and u2 prime, are going to be given by, so u1 prime is going to be negative y2 times g over the Wronskian. All right, so the Wronskian of y1 and y2. And similarly, u2 prime is going to be equal to positive y1 times g over that same Wronskian. So the Wronskian is the denominator of both of these. All right, we obviously need to integrate these to determine the actual functions u1 and u2. All right, and so then what we do is we integrate those become the coefficient functions. We just take the integral, right? And what we end up with is the following equation. And this is going to be the kind of main idea of this lecture, right? But integrating these and plugging back into 1 star. Remember, 1 star was just our guess at the solution. So we're going to plug this into 1 star. Remember, 1 star way back here was just the original guess, right? So we plug in our u1 and our u2 to 1 star. Then what we obtain is the following. equation for the solution of this non-homogeneous differential equation. So we'll get that our y of t is going to be y1 of t, I'll leave this on the outside, times u1. u1's a function, right? So u1 is going to be the integral, and I'm just going to put initial conditions here, so t naught to t, of negative y2 of s, integration variable, times g of s over the Wronskian of y1 and y2 as a function of s ds. All right, so we integrate that out, we get our function, we get some kind of a constant as well, right? So if we know a t naught, if we don't know t naught, then that's an unknown constant. Plus, then we're going to have our y2 of t times the second coefficient, right? The second coefficient is y1 of s times g of s, all divided by the Wronskian inside of the integral. So again, this is t naught to t. Integration variable is s, y1, y2 of s ds. And this right here is going to be our solution to the non-homogeneous differential equation. All right, so we'll call this 4 star. Okay, so this is where we're going to start actually. We don't need to actually derive the formula every single time. We can just start from this formula right here for the variation of parameters. If you forget it, then you have to, you have to either look it up or you have to go through this process again in your mind. But as far as we're concerned now, what we're going to do is just do a couple of examples where we use the variation of parameters method. We just plug into these integrals and we solve these things that way. Okay, so I just have 2 examples for us to do because this is the main portion of this lecture, the derivation of this formula. Let's do a couple of examples here together, and then we'll call this lecture finished. But the first example, let's start with a very straightforward one. So y double prime minus y prime minus 2y is going to be equal to 2e to the minus t. This is going to be our first example. This one we know could be solved by other methods, right? We learned the undetermined coefficient method in the last lecture, but I want to do this one by variation of parameters. So the first step is going to be to find the fundamental solution set. So step 1 is to find our y1 and y2. And of course, we also need to make sure that those are linearly independent anyway. I mean, we know how to solve those, but we need to compute the Wronskian as well. So we're going to need that as part of our solution. So find those. And then step 2 is going to be to plug into this equation 4 star to find the general solution of the non-homogeneous part. Okay, non-homogeneous equation. So why don't you guys take a moment to work on that one on your own, and then when you come back, we'll do it together. All right, let's see how you guys did. Remember, the first step is to find the homogeneous solution. So the first equation that we have to solve is y double prime minus y prime minus 2y equals 0. And of course, this has characteristic equation r squared minus r minus 2 is equal to 0. And this one is going to factor, right? So it's going to be r minus 2 times r plus 1. And so that means that our characteristic roots are r equals 2 and r equals minus 1. Okay? So that means then, and again, the order of these doesn't matter, but it's going to change the way that we plug into our equation. So once we make the decision on which one of them is y1 and which one's y2, we have to stick with that order for the rest of the method. And then, regardless of which choice you made, you will end up with the same solution as long as you stick with that order, right? So I'm going to say that y1 is going to be e to the 2t, and y2 is going to be e to the minus t. If you chose the opposite, it's okay, just wait till the end and we should have the same answer. Remember now also that we need to know our Wronskian, right? So let's take our Wronskian here of these 2 functions, and again, the order matters, so I have to stick with the order that I've chosen. So the Wronskian is going to be the determinant of the matrix for which e to the 2t, e to the minus t are in the first row, and then the second row is going to be the derivative. So 2e to the 2t and minus e to the minus t. And the determinant of this is going to be minus, these things are going to work themselves out, right? But so it's going to be e to the 2t minus t. So it's going to just be minus e to the t, right? 2t minus t, it's just t. And then it's going to be minus again 2e to the t. And so that works itself out to negative 3 e to the t. So that's our Wronskian. Okay, that's going to go in the denominator of this whole thing. Our function g is, of course, this right here, right? 2e to the minus t. So we should write that down. So our function g is 2e to the minus t. And now we can write out our solution. So I'm going to write, because we don't have an initial value problem here, I'm going to write out the integral equation a little bit differently, but not too much differently. So our solution is going to be y of t equals y1, which is e to the 2t, times u1. u1 I'm just going to write as an indefinite integral here. So it's going to be negative y2, so minus e to the minus t, times g, so times 2e to the minus t, divided by the Wronskian, which is negative 3 e to the t dt. So that indefinite integral will include a plus c. That'll give us our unknown constant for the homogeneous part, right? And then plus y2, so that's going to be e to the minus t, times the integral of, this time it's going to be positive y1, so e to the 2t, times g, which is 2 e to the minus t, over the Wronskian, which is still negative 3 e to the t dt. And so these two integrals are what need to be computed now, right? We just have to compute each of these integrals, and then we'll be done. Okay, so let's do it. Again, this is u1, right? So u1 is going to equal, I'm going to do these separately, and then we'll plug them back into this equation. But after some simplification, the minus signs cancel, right? The 2/3 can come all the way out, and then the integral is going to just be e to the minus 1, 2, 3, right? E to the minus 3 t dt. And so when we integrate this, this becomes a minus 2/9, actually, right? So negative 1/3 comes out, e to the minus 3t plus c1. Okay? Our u2 is, of course, this one over here. We can do the same thing here, and then we'll put it all back together. Again, the 2/3 comes out. This time it's negative as it comes out. So negative 2/3. This one is then the integral of 2t minus 1t minus another t. So that what's left in here is just a 1, right? So the negative 2/3 comes out. The exponentials all cancel here, and we're left with a 1 dt. And so this one's going to be negative 2/3 times t plus c2. Okay? These now get plugged back into our solution, and our final solution here, our solution of the non-homogeneous part, is going to be y of t equals e to the 2t times all of this, right? So, and then I'll rewrite this again, but times negative 2/9 e to the minus 3t plus c1, and then plus e to the minus t times this portion, right? Negative 2/3 times t plus c2. All right, and so just combining all of this, our final answer will be that this is going to be negative 2/9 e to the minus t plus, turns out to be negative, right, minus 2/3 t e to the minus t. So there's the non-homogeneous part, and then plus these two answers here, right? c1 e to the 2t plus c2 e to the minus t. Okay, and so that is our solution to the non-homogeneous differential equation given right here, right? The non-homogeneous differential equation using variation of parameters. All right, I've got one more example for us to do, and then we'll leave this lecture here. Like I said, just a couple examples of this. This one, I would like us to solve the following non-homogeneous DE, differential equation. Again, this one's going to be not an initial value problem, it's just a differential equation. But this one's going to be x squared y double prime. So this has got x as the independent variable as opposed to t. So our solution will be y of x. So x squared y double prime minus 3x y prime plus 4 times y. And on the right-hand side, this is going to equal x squared times the natural log of x. So again, this one, if we're very careful, you could do this one by undetermined coefficients. Again, if you're very careful. But let's do this one by variation of parameters. Again, I want you to pause the video and try this one on your own before we do it together. But what I would say as a hint, right, is that you first have to solve the homogeneous equation. So you have to think about what kind of equation that is once you make it homogeneous. And then once you have those solutions, then you need to go through and you need to get this in the proper form. Okay, so right now this has an x squared as a coefficient in the front. If we go all the way back to our initial setup, our solution, 4 star, in this big box here, this solution only works if the original differential equation is in this form, right? So if it has a coefficient of just a 1 in front of the y double prime. All right, so keep that in mind. Give this a good shot. Get as far as you can, and then when you come back, we'll do it together and check your work. Okay, let's see how you guys did. I'm not going to do the homogeneous part, but I hope that you notice. I'll write it down, and I'll write down the solutions, of course. We need those. But I hope you notice that the homogeneous portion, if you write x squared y double prime minus 3xy prime plus 4y equals 0, that this is an Euler equation, right? So this is an Euler equation. And we have a method for solving the Euler equation. And what you should end up with after solving this Euler equation, so if you got stuck on that part, take a moment now, pause, and try to solve this Euler equation as such. But what you'll end up with are the two solutions, the fundamental solutions of x squared, and then y2 is x squared again. So when you get a repeated root with an Euler equation, you multiply by natural log. I hope you remember. So x squared and x squared natural log of x. All right. So let's now use these to solve our non-homogeneous equation using the variation of parameters method. All right. Again, we need to divide through, but we also need to know the Wronskian. So let's start with the Wronskian of our y1 and our y2. And again, in this order, once we choose the order, we have to stick with it, right? So the Wronskian function is going to be x squared here, x squared natural log x here. Take the derivatives, 2x. This one's going to be 2x natural log x plus just x, right? X squared over x. So it's just x. By the way, we have to, x can't be 0 here, right? So we're assuming that x is positive in this scenario, as I've left off any absolute values on the natural log. All right, but now when we compute this, we're going to see this times this minus this times this. Those are gone, and all we'll be left with is this one. But let's write it out. So this will be x. Let's write out all the terms here, right? So it's going to be 2x cubed natural log x plus x cubed minus 2x cubed natural log of x. And so these, of course, will cancel and leave us with just x cubed. All right. So again, now we want to, so that's our Wronskian. We need that. We need our y1, we need our y2, we need our Wronskian. We also need our g, right? But this is not g, if you look at this equation, because what we need to do is get it in the right form, and that means dividing everything through by the leading coefficient function, which is going to be our x squared, right? And so what we end up with is that our g of x for this function is just the natural log of x. Okay? It's natural log of x. So now we can plug in and write down our solutions. So our function y of t is going to be u1, it's going to be y of x though, right? Independent variable is x here. So y of x is going to be u1 of x times x squared, y1, right? Plus u2 of x times x squared natural log of x, that's y2. And then I'm going to write down the formulas for the u's down here, and we'll work them out separately. So u1 is, of course, the integral of negative y2, so that's going to be x squared ln x, times g of x, which is natural log of x. I'm going to write it here. So g is just natural log x, right? So g, yep. So that's natural log of x divided by the Wronskian, which is x cubed. And this is all dx. So this one, the minus sign can come out. And then we're left with, in here, a natural log of x, quantity squared, over x dx. And this is, of course, if we make u substitution, we could just do it in our mind, because natural log of x, its differential, dx, is 1 over x dx, right? So this is just a u squared du. So this one's going to be minus 1/3 natural log of x quantity cubed plus c1. Okay, so that's negative 1/3 natural log of x quantity cubed plus c1. All right, our u2, we have to follow the same kind of method here, right? u2 is positive y1, so that's x squared, times g of x, that's our natural log of x, divided by the Wronskian, x cubed dx. So this one's just going to be the integral of natural log of x over x dx. Very similar, right, to what we've just done, but this one is just going to be 1/2 x ln of x squared, right? So 1/2 natural log of x quantity squared plus c2. All right. Now we have to plug in, right? We plug back into our solution here, and I will divide this up. Well, let's write it out in 2 steps, just to make sure we get all the parts, right? So this is going to be, I will separate this part out with the homogeneous part as we go along. So this one's going to be negative 1/3 x squared times the natural log of x quantity cubed. All right, and then we'll plug this one in here. So this is then going to be plus 1/2 x squared natural log of x also cubed, because there's 1 here and 2 here, right? So plus 1/2 x squared natural log of x quantity cubed. Then we'll have our homogeneous part, which is plus c1 x squared plus c2 x squared natural log of x. We're almost done, right? The last thing we can do is just notice that these two can be combined into a single term because they have the same function, just different coefficients. And so our solution, our general solution to this non-homogeneous differential equation is going to be, so 1/2 minus 1/3 is 1/6, right? So this will be 1/6 x squared times the natural log of x quantity cubed plus the homogeneous solution. So c1 x squared plus c2 x squared natural log of x. And that's it right there. That's our solution. Not too bad, right, as you go through this, provided you don't miss any of the steps, right? We have to do all the steps, get it in the right form, and then a couple of integrals, and we've got our solution. So I'm going to leave this lecture here, and hope you guys enjoyed it, and I'll see you in the next one.